Calorimetry under constant pressure and constant volume conditions. Okay, so we've talked about enthalpy for quite a while now, and we know that enthalpy is the heat of reaction, or the heat released or absorbed during a reaction. Now, calorimetry is a means to measure that heat transfer during chemical or physical processes. Now, it's hard to measure heat, quote-unquote heat itself, so we measure it in terms of temperature changes. We set up experiments where we're able to relate temperature changes to the heat released or absorbed during a reaction. Now, in a calorimetric experiment, the heat lost or gained in the reaction is related to the temperature change of the calorimeter. Okay? So the heat absorbed by the calorimeter is exactly equal to the amount of heat released by the reaction. So that's where we get the opposite sign. Okay, so heat released by the reaction going into the calorimeter. Now, as you can see in the equation, that amount of heat is exactly the same. It's exactly equal to the amount of heat released by the reaction and absorbed by the calorimeter, or the other way around. The reaction may absorb heat and then the calorimeter would release heat. Okay? So, but they're always the same quantity, just opposite in sign. Okay, now when heat flows into an object, it does make sense to us that its temperature would increase. But how much that temperature increase is, or how much that temperature goes up, is dependent on the heat capacity. So what is the heat capacity? So it's basically the amount of heat required to raise the temperature of something. So it can be a calorimeter, it can be water, it can be, any particular thing, 1 Kelvin or 1 degree C. Okay? And so one equation for heat is Q is equal to the heat capacity, capital C, times delta T. And delta T is just this temperature change we've been talking about. So T final minus T initial. All right, and this is the heat capacity of some object. Okay, so we're going to use this particular equation we're going to use in a bomb calorimetry experiment a little bit later. Okay, so another type of heat capacity is called the specific heat capacity. And you also might hear this called specific heat. And this is the quantity of heat required to raise the temperature of 1 gram of a substance, 1 Kelvin or 1 degree C. Okay? And so notice in this case, here's our specific heat capacity, and we're going to multiply it by the mass and this temperature change, and that's going to give us the amount of heat released or absorbed by the process. Okay? Now, specific heats are found in a table, so you would look them up for a given material. All right, and the last kind of heat capacity that we're going to talk about is the molar heat capacity. And so this is just the amount of heat required to raise the temperature of 1 mole of a substance, 1 Kelvin or 1 degree C. And so again, this equation looks similar to the specific heat capacity equation. So we have moles times our molar heat capacity and this change in temperature. Okay? And again, molar heat capacities are also found in a table. So you would look them up for each specific material. Okay, so we're going to talk about 2 different types of calorimetry experiments. The first one uses something called a bomb calorimeter, and that is a calorimeter that maintains constant volume during some process. So for instance, it has really rigid walls, and so no matter what happens inside there, that volume is not going to change. Okay? So we call this constant volume calorimetry or bomb calorimetry. The other type of calorimetry is called constant pressure calorimetry. And one of the most common forms of this, at least in general chemistry labs for students, is something called coffee cup calorimetry. And basically, constant pressure calorimetry is the type of calorimetry you would do on the desktop. The pressure remains constant. We just have atmospheric pressure on our system, but volume changes may occur. Okay, so constant pressure calorimetry is the most common form. Bomb calorimetry, you need a very special setup for that. Okay, so let's talk about bomb calorimeters first. And basically these maintain constant volume, as we've said, and because that volume is constant, no PV work is done during the process. So there's no volume change, no PV work is done. So we are actually measuring the change in internal energy for that reaction, delta U. Okay, so just reminding ourselves, okay, so remember that delta U is equal to the heat plus the work, okay? And one equation for work is negative P external, so that's external pressure times our change in volume. For our closed calorimeter system, delta U is equal to 0. And if delta V is equal to 0, then no work is done. Okay, so plug in that 0 and we just get heat at constant volume, which is equal to delta U. Okay, now here's the form of the equation that we use with bomb calorimeters. See, this capital C is actually the heat capacity of the bomb calorimeter itself. So that includes everything. The material the walls are made out of, the water, everything. So that's the heat capacity of the bomb calorimeter. Okay, so here's a little schematic showing one. Okay, so here we have some sort of rigid container, okay, and we filled it with water. And inside we have a cavity for reactants, so some sort of little holding area where we can put our reactants. We have a thermometer to measure the temperature change during the reaction. And in order to get the reaction to go, we're going to have some sort of ignition source that's going to start that reaction, okay? And basically, bomb calorimeters are usually used when one of the reactants is a gas, okay? And again, the bomb is made of rigid materials and includes a cavity for the reactants. And also remember that capital C in this equation is the heat capacity for the whole calorimeter, for the whole thing. Okay, so if we react 0.05 mole of hydrogen gas and 0.25 moles of oxygen gas according to this equation, then we are going to measure a temperature change, okay? Our heat capacity of our calorimeter is 90.6 kilojoules per mole, and we got that by calibrating it. And the initial temperature, we start off at 25.000 degrees C, okay? We ignite the reaction, kaboom, and the temperature increases to 25.155 degrees C. Okay, so we want to calculate Q for this reaction. So we want to calculate the heat. Okay, now let's get delta T first. Okay, so T final minus T initial. So we went from 25.000 degrees C to 25.155 degrees C. Okay, that should be a 5 right there. And we ended up with a delta T of 0.155 degrees C. Now if we plug all that in, then here's our heat capacity of our whole bomb calorimeter, okay, and our temperature change, and we're going to get 14.0 kilojoules. All right, so that was pretty easy math, but what actually happened here? Okay, so was heat absorbed or released by the reaction itself? Okay. All right, so let's think about this. Now the temperature of the calorimeter increased. So what does that tell us? That heat flowed out of the reaction and into the calorimeter. Okay? So that means the reaction is exothermic. Heat flowed out of the reaction and into the calorimeter, increasing its temperature. Okay, so constant pressure calorimetry. Now remember, delta H is just the heat at constant pressure. Okay, and we discussed that in a previous video also. And so constant pressure calorimeters measure delta H directly. Okay, so we can directly measure the change in enthalpy for the process using a constant pressure calorimeter. And again, one of the most common kinds as far as general chemistry students is concerned is a coffee cup calorimeter. Okay, so what we have here are two styrofoam cups, okay, nested inside each other. And inside the second one, we have a water bath, okay, with a certain amount of water, and we know how much that is. We've also added perhaps some sort of substance to dissolve. So we're going to see an example of that in a second. So we have our reaction mixture. We have a thermometer and an insulated stopper, okay, and something to stir the reaction, okay? Now, because these coffee cups are nested, then that provides some insulation, so we can say that no heat is lost to the surroundings. Okay, so here's our delta H reaction, which is equal to the heat of reaction. Okay, so we know that, and we know that this heat of reaction is equal to the heat of the calorimeter except opposite in sign. Okay, and so we can actually get the heat of reaction by calculating the mass of our reaction mixture times its specific heat capacity and the temperature change that we measure. Okay, so in this way we can actually get to this heat of reaction by measuring how much the temperature changes during the reaction. And since we've made this reaction mixture ourselves, we know what it is, so it's heat capacity, and we know how much there is. Okay, so here's an example for you to try. A student built a coffee cup calorimeter using 100 milliliters of water. 4.95 grams of solid potassium hydroxide was then added to the water. As the potassium hydroxide dissolved into solution, the temperature of the solution increased from 23.0 degrees C to 34.5 degrees C. So we want to calculate delta H reaction. Now, you can assume the density of water is 1 gram per milliliter, and its specific heat capacity is 4.184 joules per gram degree C. Okay, so before we start with calculations, let's think about where we're going and the concepts involved. Okay, so first off, what are we measuring? What's the reaction? Okay. And so we are measuring the heat change during the dissolution of potassium hydroxide in water. Okay? Now, the temperature of the solution in the calorimeter increased. So heat was absorbed by the solution in the calorimeter. So knowing this, is that dissolution reaction releasing or absorbing heat? Is it exo or endothermic? Okay, so think about that for a second. So that temperature of the solution increased. What does that tell you about whether heat was released or absorbed? So it should tell you that heat was released during the reaction and absorbed into the solution. So that reaction is exothermic. Okay? So now, this heat absorbed by the calorimeter, which is our water solution, the potassium hydroxide and the water, we can calculate that heat using the mass times the specific heat capacity times that change in temperature that we measured. And that heat absorbed is going to be equal to the heat released by the reaction. Okay? And so this gives us our delta H reaction. Okay, so now we're ready to start calculating. So let's find the heat absorbed by the calorimeter first. Okay, so we're going to use this equation. The heat of the calorimeter, the heat the calorimeter absorbed, is equal to the mass of the solution times the specific heat capacity of that solution times its temperature change during the process. Now, the mass of the calorimeter solution is the mass of the water plus the mass of the potassium hydroxide dissolved. Okay, so let's take our 100 milliliters of water. We're going to use the density of water to convert that to mass. So we have 100 grams of water plus our 4.95 grams of potassium hydroxide to give us 104.95 grams of solution. So that's our M. That goes right here. Okay? All right. So now that we have our mass of solution, we're going to go ahead and use our assumption that the specific heat capacity of water, and we can even make this assumption for the solution because the solution is dilute. So the specific heat capacity is essentially that of water. So we're going to use 4.184 joules per gram degree C. Okay, and next we're going to calculate this change in temperature. Okay, so we saw that the solution went from 23 degrees C to 34.5. Okay, so 34.5 is T final minus 23.0. We get 11.5 degrees C. And now we're ready to plug everything in. So 104.95 grams, so that's the mass of our solution, times its heat capacity, times the temperature change, and we end up with 5,049.8 joules, which will then round to 5,050 joules. So that's the heat absorbed by that calorimeter solution. Now that heat absorbed is exactly equal to the heat released by the reaction if we assume that no heat was lost to the surroundings. Okay, so opposite sign, same magnitude. Okay, so the heat of the reaction was negative 5,050 joules, so that was the amount of heat released. So the delta H of the reaction was negative 5,050, okay, or 5.05 kilojoules. Now we only need 3 sig figs, so let's go ahead and round the kilojoules to 5.05 kilojoules for delta H reaction. Okay, now this experiment showed us that 5.05 kilojoules was released when 4.95 grams of potassium hydroxide was dissolved into 100 milliliters of water. Now, how could we use our result to figure out how much heat is released when 1 mole of potassium hydroxide is dissolved into solution? Okay, now we can use our heat released from that small amount of potassium hydroxide, because we know how much heat that produces. We can actually use that as a conversion factor to figure out how much heat would be released if we dissolved a whole mole. Okay, so if we calculate the molar mass for potassium hydroxide, then we end up with 56.11 grams per mole. Okay, and so now let's go ahead and use our heat that we measured, the heat released for the amount of substance dissolved. We're going to use that as a conversion factor. So we have 56.11 grams per mole for 4.95 grams of potassium hydroxide. The reaction released 5.05 kilojoules. And so we're going to cross out our grams because those are canceled out. We're going to end up with kilojoules per mole. And if we do this math, 56.11 times 5.05 divided by 4.95, we're going to end up with negative 57.2 kilojoules per mole of potassium hydroxide dissolved. So this is the enthalpy of solution. So the enthalpy when you dissolve potassium hydroxide into solution. And this is for a whole mole. So see how we didn't even have to dissolve a whole mole in solution and measure it. We can do a little bit, figure out how much heat was released from dissolving that little bit, and then use it to calculate the enthalpy of solution for a whole mole. Okay, so let's summarize some of these calorimetry concepts, because there are a lot of things going on in this. And calorimetry is basically a means to measure heat transfer during a reaction. Okay, calorimeters are designed so that they minimize heat loss to the surroundings. And that way we can relate the observed temperature change in the calorimeter to the reaction occurring. Now the amount of heat absorbed by the calorimeter is the same as the amount of heat released during the reaction if we assume that no heat is lost to the surroundings. And we could also say that the amount of heat released by the calorimeter is the same as the amount of heat absorbed during the reaction for an endothermic reaction, also assuming that no heat is lost. Okay, so the heat of the calorimeter is equal in magnitude to the heat of reaction with opposite sign. For an exothermic reaction at constant pressure, so remember we are measuring enthalpy of reaction, or delta H, heat is released by the reaction and absorbed by the calorimeter. Okay, so Q calorimeter is equal to negative delta H reaction. For an endothermic reaction at constant pressure, now heat is absorbed by the reaction from the calorimeter. Okay, so negative Q calorimeter is equal to delta H reaction. Okay, for an endothermic reaction. Now, would the temperature of the calorimeter increase or decrease for an endothermic reaction? So think about that for a second, and then I'll tell you the answer. All right, so if you were thinking that the temperature of the calorimeter would decrease, then you would be correct. So heat would be going out of the calorimeter and into the reaction. The reaction is absorbing heat from the calorimeter, and so the calorimeter temperature would decrease. Okay, so in a constant pressure calorimetry experiment, we can measure the heat transfer for a small amount of reactant and then use our result to calculate the molar enthalpy, which is the amount of heat released or absorbed by a mole of the substance. So that's what we did in our final example in the coffee cup calorimeter. We measured the heat released by dissolving 4.95 grams of potassium hydroxide into water, and then we used our result, the amount of heat that we calculated from that reaction, as a conversion factor to figure out how much heat would be released by dissolving a whole mole of the substance. Okay? Now remember, the heat under constant volume conditions is equal to delta U. That's bomb calorimetry. And the heat under constant pressure conditions is equal to delta H. Okay, and this is the usual situation. All right, so what you should be able to do. So you should be able to describe how a calorimetry experiment is used to measure heat transfer. So describe the process, sketch 1, sketch calorimeters, okay? You should be able to describe the differences between bomb and constant pressure calorimetry. And you should know which thermodynamic state function they measure, either delta U or delta H. You should be able to perform calculations involving calorimetry. Okay, so there are lots of example problems that we can do, and I will be posting more of those. And you should also be able to identify and justify whether energy, or in the form of heat, was released or absorbed by the reaction during a calorimetry experiment, based on what you observe happening to the temperature of the calorimeter.